Hello, class. This is chapter 4's lecture. I thank you for being with me today. So let's get started. Let me share my screen so that you can see the PowerPoint presentation and the worksheet. All right, so you should be able to see the PowerPoint presentation now. And so once again, this is on chapter 4, which is on variability, a very crucial and important component to the foundation of all the statistics that we're going to learn in the upcoming weeks. So, what are some of the learning outcomes? What should you know by the end of this chapter? Well, you should understand the purpose of measuring variability, why it's important, and why we do this as researchers who are using statistics. We are not going to cover the range or computing the range, but you're more than welcome to review it in your textbook. I do want you, however, to understand what the variance and what the standard deviation mean and how to calculate those two statistics along with SS, which is the sum of the squared deviations, and how to do it for both a population and for a sample. All right. So some of the tools that you're going to need in order to be successful in this particular chapter, like I said last lecture, everything in statistics, at least in this class, is going to build off of the previous week. So you're going to have to be comfortable with the summation notation, which by now you probably should be. You're also going to have to be pretty comfortable with the two of the measures of central tendency, and that being the mean and the median, with the mean being the main thing that you need to be comfortable with. All right, because everything that we're learning this week revolves around the mean. So an introduction to variability. So, variability, we could define it in a couple of different ways, right? One way to measure variability, and if you look at the word variability, the root word to that is variable, which means things that can change, right? So variability could be defined in a couple of ways. One is that it's a quantitative, a numerical distance that that measure a numerical way to measure distance based on the differences between scores. Another way to kind of describe it is that it describes the distance or what we call the spread of scores from the mean. All right. So basically, variability is, hey, how far away are scores from other scores in the population or the sample? And how far away, as far as distance is concerned, how far away are scores from the mean? And so the purpose on why we measure variability is it helps us to describe the distribution that we are working with. By knowing the mean and the standard deviation, we can figure out relatively easily if the scores are all clustered together. And I'm going to show you a picture of what that looks like. Or if the scores are really spread out. And when I say cluster to spread out, I mean cluster to spread out from the mean. Another purpose is just to measure how well an individual score represents the distribution. And we're going to work on all of those as we move forward. So once again, usually variability is going to be defined in terms of distance, right? So it tells how much distance to expect between one score and another, or how much difference to expect between an individual score and the mean. For example, we know that the heights for most adult males are clustered close together. They're within 5 or 6 inches of the average mean for height. Although more extreme heights do exist, right? They are relatively rare. And so this aspect of variability is very important for inferential statistics, all right, in which relatively small samples are going to be used to answer questions about large populations. For example, suppose that you selected one person to represent the entire population. Because most adult males have heights that are within a few inches of each other, or within a few inches of the population average, right? The distances between heights are small. So there's a very good chance that you would select someone whose height is within, let's say, 6 inches of the population mean. On the other hand, the scores are much more spread out, meaning that there's a greater distance between the scores in the distribution of weights, right? So in this case, you probably would not obtain someone whose weight was within 6 pounds of the population mean. So the variability provides information about how much error to expect if you are using a sample to represent a population. And so here is a figure kind of showing what we mean by distributions being clustered or spread out. So here are the height of adults in inches for, let's say, for males, right? And so the average population height is 70 inches, right? But the scores, right, the various heights are all clustered, meaning that they're close to this mean, right, of 70, right? We have some people who are a little bit shorter, who are, 58 inches, some people who are a little bit taller, 82 inches, but they are relatively close to the mean, right? And so we would say that this distribution, the scores are clustered close to the mean, right? And that's for height, right? There's not a big variability in height. Obviously, there's extremes, right? Somebody like Shaq, who's like 7 foot, 1 or 2, they're out there, but they don't represent a large quantity of the population. Nor is little people, right? Those who are experiencing dwarfism, right? They're really, really short, right? But they don't make up a large part of the population. The majority of people are, very, very close to this population mean of 70 when we're measuring adult height in inches. Now, if we look at a distribution where the scores are very spread out, well, like the example I talked about in the last slide, we could use weight. So this is adult weights in pounds. So the average, the population mean for adult weights is 170. Let's say this is for for men, right? Or let's say it's for women. If you wanted to pick somebody out of here, right? Because the weight distribution is so wide, right? We probably wouldn't be able to pick one person out of this population that is very, very close to the adult population mean, right? You could have people who are 110 pounds, which is really far away from 170. You could have people who are 230 pounds or more, right? So the distribution of the scores, right, for this population are very spread out. They're very far from the mean, all right? So if the scores in a distribution are all the same, right? Let's say that all the scores were the same in the distribution, then there would be no variability because nothing would be varying. Everything would be the same, right? But if there are small differences between scores, then the variability is going to be small. And if there are large differences between scores, then the variability is going to be large. So we're going to talk about two measures of variability. One is what's called the variance, and the other is called the standard deviation. So how are we going to define the variance and the standard deviation? So the most common, right, most common, at least in statistics, and the most important measure of variability is going to be the standard deviation. And what the standard deviation is, it's a measure of the standard or the average distance from the mean. So what we use it for is it's going to describe whether the scores, right, are clustered closely around the mean or are widely scattered, right? So the calculation to do this standard deviation statistic is going to, or parameter is going to be, it's going to differ if we have a population or a sample. And I'm going to show you how to do both. Now, when it comes to the variance, variance is when we're on the route to calculating standard deviation, we're going to calculate the variance. And the variance is also a measure of variability, but it is not the same concept as standard deviation. So let's look at how we do this, right? So when we're trying to calculate the standard deviation, right, I'm going to outline the steps for you, and then we're going to work on a problem or two with this. All right. So the step one, first, we're going to determine the deviation. Now, deviation, the root word of deviation means deviate. So, so deviation is the distance from the mean, right? So how much a score deviates or is different from the mean. So you get a deviation score. The deviation score is going to be the score, right, minus the population mean. All right. So this assumes that you've already calculated the population mean, so you know how to get this deviation score, right? So you take each score and you subtract the population mean from it. All right. And now step two, right, is you're going to find what is called a sum of deviations to use as a basis for finding an average deviation. However, you run into some problems, namely two, right? Deviations, right? These deviation scores, if you add them all up, they are going to add up to zero, right? And we kind of covered this last week, but I didn't explicitly state it, but that's because the mean is a balance point, right? So if we do that, if we just add them all up to zero, right? It is going to be if we add up all the deviation scores, they're going to add up to zero. All right. So now, if the sum is always zero, then the mean deviation is going to be zero. All right. So we're going to need a new strategy, but keep that problem in mind. We're going to talk about that problem a little bit more. So if we revise step two, what we do is we are going to remove the negative deviations. All right. So how we do that is we're going to square each deviation score. And then once we have squared each deviation score, we are going to add up all of those squared deviations. And the sum of those squared deviations is called SS. All right, it's called SS. And that is an important statistical concept in its own right. And we're going to learn how to do a couple of different calculations for it. Give me 1 second, y'all. 1 second. So this SS is important. All right. All right. So now step 3. We are going to average the squared deviations. And the mean squared deviation, so once we get that average of the squared deviations, that is what we call the variance. All right, that's the variance. And it is the variability in squared units. All right, so the population variance is going to equal the mean squared deviation of the scores from the population mean. All right. So we still have one extra step, right? Because we calculated the variance, but we need the standard deviation. So we're going to move to step 4. All right. And for step 4, our goal is again, our goal is to compute a measure of the standard or the average distance of the scores from the mean. But the variance is the average squared distance from the mean. And that's not really what we're looking for. All right. So to adjust for having squared all the differences, right, we are going to take the square root of the variance. And the square root of the variance is going to give us our standard deviation, or our average distance a score is from the mean. All right. So just to kind of put into more perspective the difference between the variance and the standard deviation, the concept of square distance, right, which is what the variance is describing, our average square distance. It's not an intuitive or an easy concept to understand. For example, it isn't particularly useful to know that the square distance from New York City to Boston is 26,244 miles squared or whatever, right? The squared value becomes pretty meaningful if you take the square root of it, right? So for example, the distance from New York City to Boston is the square root of 26,244, which equals 162 miles. Now it becomes pretty obvious just how far away, Boston is from New York, right? So we got to remember that these terms are distance from the mean, all right? And they're only used with numerical scores. So we're going to be using these with, again, like we talked about last week and prior weeks, interval and ratio scales of measurement, all right? Okay, so let's look at the calculation of this. Well, let's look at a flow chart of how we got to this, right? So first, we're going to find the deviation, the distance from the mean for each score, right? Now, if we add those deviations, right, that should come up to 0. And so our standard deviation would be 0. So that's a dead end. So we don't want to do that. So instead, we're going to find the deviation, so the distance from the mean for each score, right? So we're going to take each score and subtract the mean from it. And then we're going to square each of those deviation scores. Then we're going to add all those deviation scores up and divide by the number of scores that we have. And that is going to be called the variance. And that is the average of the squared deviations. All right, but we're not done yet. After we get that variance, we're going to take the square root of the variance to get what we wanted all along, which is our standard deviation, which again, the standard deviation is the standard distance or the average distance a score is from the mean. All right. So that is standard deviation and variance. So let's look at the calculation of it. So in this example, it says, hey, we're going to calculate the variance and the standard deviation for the following population of scores. So we know this is dealing with a population because there's a capital italicized N, and it says, hey, this is the population, right? There's 5 scores in the population, right? And so remember, right, that the purpose of the standard deviation is going to be to measure the standard distance from the mean. So first, we got to begin by calculating the mean, right? So 1 plus 9 plus 5 plus 8 plus 7 is going to give us 30. And we're going to take that 30 and divide by the number of scores that we have, which is 5. And so that gives us a mean of 6. All right. So next, we're going to find the deviation scores, the distance from the mean for each score, and then we're going to square the deviations. All right, so if we use the population mean of 6, right? Remember this symbol right here means mu. It stands for the population mean. The calculations are as follows. So here are the scores: 1, 9, 5, 8, and 7, right? We're going to take the mean and subtract it from each score. So 1 minus 6 gives us -5. 9 minus 6 gives us 3. 5 minus 6 gives us -1. 8 minus 6 gives us 2. And 7 minus 6 gives us 1. All right. Now, if we were to add all of these up, right, this is going to add up to 0, right? -5 plus -1 equals -6. 3 plus 2 plus 1 equals 6. -6 plus +6 gives us 0. All right. So if we had a 0, then the mean, then the standard deviation would end up being 0. And so that wouldn't be very helpful. So what we do instead is we square those deviation scores. We square it. So -5 squared is 25. 3 squared is 9. -1 squared is 1. 2 squared is 4. And 1 squared is 1. And what this does is it gets rid of the negative signs and allows us to continue with the calculation. All right, so once we have squared each of those deviation scores, we're going to add those deviation scores up, all right? And that is what is called the sum of squared deviations. And the notation for that is going to be SS, all right? But we're not done yet. We don't just need the sum of the square deviations. What we're looking for is the standard deviation. So we have 2 more steps to go, right? If we take the sum of the squared deviations and divide it by the number of squared deviation scores, or in this case is 5, this is going to be 40 divided by 5 equals 8. 8 is going to be the variance, which again, the variance is the average squared deviation of scores from the mean. It's not quite what we're looking for, like I just talked about last slide. So we have one more step. We're going to take the variance and take the square root of it. So the square root of the variance, which was 8, gives us 2.83. 2.83 is the standard deviation, or the average distance a score is from the mean. So if we go on average, right? If you think about it a different way, on average, how far away is the scores in our population from the mean? Well, on average, the scores in our population are about 2.83 distance points from the mean. All right. And that's kind of what the standard deviation is letting us know. Okay. So let's look at and go through some problems to kind of help kind of do this in sort of real time. So I'm going to skip question 1 because we kind of, talked about that already. So in this one, it says number 2, the deviation scores, right, are calculated for each individual in a population of 4 scores. The first 3 individuals have deviations of +2, +4, and -1. What is the deviation for the 4th individual, right? So if we add up deviation scores, right, the sum of those should add up to 0, right? So if we have +2, +4, and -1, well, that comes up to what? That's 2 plus 4 is 6. 6 minus 1 is 5, right? So if this has to add up to 0 and we have one more score, then we need a score of -5 in order to make this 0, right? So the answer here is -5 because the sum of deviation scores is always going to equal 0. Always going to equal 0. Okay. So question 3, what is the standard deviation for the following set of scores? And now we know we're dealing with a population because we have a capital italicized N. So in this population of 5 scores, all the scores are 10, right? And so this kind of gives you, the lesson kind of gives you a hint. It says, hey, you should be able to answer this question directly from the definition of the standard deviation. So the standard deviation, we don't have to do any calculations for this. The standard deviation is measuring, on average, how far away are scores from the mean. Well, if all the scores are the same, then the mean, right? Think about it, the mean is going to be 10, right? And all the scores are 10. So the standard deviation is going to be 0, right? Because nothing is varying. Everything is the same, right? The standard deviation is measuring how, on average, how far away is a score from the mean. Well, all the scores are equal to the mean. So the standard deviation is 0. All right, it's 0. All right, and so the last question is compute the variance for the following population of scores. All right, so let's do that. Okay. Sorry about that sound. Hopefully you couldn't hear that. Let's bring up. All right, so let's calculate the variance. So what I have done is I've made a worksheet for the majority of the chapters that we have and the majority of lectures that we're working on to kind of help you be able to go step by step through the process of a lot of these questions. All right, so if in this question, let me give me a second. Okay. So I was going to kind of cover this, right? So if you follow along by what number it is, it'll take you step by step. So one is you're going to list out the scores, right, that you have. In this case, we have, let me use my, in this case, we have 4, right? We have 0, we have 7, we have 1, and we have 3. Just want to reconfirm that's the right numbers: 4, 0, 7, 1, and 3. Yes. All right. So the second step, once you listed the scores out, well, how many scores do you have? What's your population of scores? Number of scores in the population? Well, it's 1, 2, 3, 4, 5. So we have 5 in our population. So n equals 5. Third step is we got to calculate. Third step is that we're going to calculate the. Give me a second. Is we're going to calculate the sum of all those scores. So 4 plus 0 plus 7 plus 1 plus 3 is going to give us 15. And then we need the population mean because we have to take a deviation score in the next step, right? So the population mean is going to be the sum of our scores divided by the number of scores that we have. So it's 15 divided by 5, which is going to give us 3. So now we move over to step 5, right? Step 5 is we're going to get a deviation score for each of our scores. So 4 minus 5 gives us 1. 0 minus 5, I'm sorry. Let's go back, rewind. 4 minus the mean, which is 3. 4 minus 3 gives us 1. 0 minus the mean, which is 3. So 0 minus 3 is going to give us -3. 7 minus the mean, which is again 3, is going to give us 4. 1 minus 3 is going to give us -2. 3 minus 3 is going to give us 0. So now, these are the deviation scores. In order to make sure that you did the calculations right, we know that if we sum up all the deviation scores, it's going to give us 0, right? This one right here, it's going to give us 0. So let's add this up to confirm this. So the easiest way to do this is by adding the positive numbers and also then adding the negative numbers, and those two should be the same absolute value, so it should equal 0. All right, so we have -3 and -2 gives us a -5, and 1 plus 4 plus 0 gives us 5. So 5 plus -5 gives us 0. So we know that we did our calculations correctly. So we can continue. So now on to step 6. In step 6, we are going to square our deviation scores. So the first deviation score is 1. So 1 squared is 1. -3 squared is 9 because a negative times a negative is a positive. All right. 4 squared gives us 16. -2 squared gives us 4. And 0 squared gives us 0. All right. Now, step 7 asks us to add up all of those squared deviations. And what we'll get for that is we're going to get what's called SS, or the sum of squared deviations. So if we add 1 plus 9 plus 16 plus 4, right, that is going to give us 30. All right. So I think our question asks us, what does the question ask? Oh, the question asks for the variance. All right, so our sum of squares, sum of squared deviations is 30. To get our variance, all right, we're going to take the sum of the squared deviations and divide by the number of scores, which was 5. So 30 divided by 5, right, is going to give us 6, right? So our population variance is 6. Now, the question doesn't ask us to do this, but let's continue with it. If we wanted to know what the population standard deviation was, right, we would take the square root of 6, which is the variance. Take the square root of the variance. And that is going to give us, square root of 6 is going to be 2.5. So that is our population standard deviation. But the answer to the question was just, what is the population variance? And the population variance is going to be 6. All right. So that is how you calculate the variance and the standard deviation, all right, for a population of scores. And here is the answers. Here are the answers. All right. Give me a second. Okay, give me 1 second. All right, so measuring the variance and the standard deviation for a population. So again, the variance equals the sum of the squared deviations, or SS, divided by the number of scores. SS, the sum of squares, is the sum of the squared deviations of scores from the mean. And so there are going to be two formulas that we have for computing the sum of squares. So it's usually called this the sum of squares, but it's really the sum of squared deviations. All right. So here are the two formulas for calculating the sum of squared deviations, or the sum of squares. All right. The first one is the formula that we've been using to calculate the variance and the standard deviation, right? So what we're doing is we're finding each deviation score, then we're squaring each deviation score, and then we're finding the sum of the squared deviations. And so this is what this formula is stating, right? This is what we've been doing before we go to the next step of calculating the variance and calculating the standard deviation. But there's another formula, right? There is what's called the computational formula. And in this one, we're going to square each score and sum those squared scores. We're also going to find the sum of the scores, square it, and then divide by the number of scores in our population. And then we're going to subtract the second part from the first. And this is what this means, you know, algebraically, right? These two formulas are equivalent, all right? But we're going to use them when different scenarios appear, all right? So one of the reasons that there are two formulas, right, is because the definitional formula is going to be awkward to use, especially if the mean includes a fraction or a decimal value, all right? So if you have a small group of scores and the mean is a whole number, then it's easier to use the definitional formula. However, if the mean ends up being a fraction or a decimal value, or you have a lot of numbers, a lot of scores, then it would be easier for you to calculate the sum of squares using the computational formula. All right. So let's go over some problems looking at that. All right. So let's calculate the sum of squares using the definitional formula. All right. So in this one, we have 4 scores, 1, 0, 6, and 1, right? And we have to calculate our mean in order to calculate our deviation scores, right? So there, 1 plus 0 plus 6 plus 1 gives us 8. 8 divided by the number of scores, which is 4, gives us 2. So our population mean is 2. So 1 minus 2 gives us -1. 0 minus 2 gives us -2. 6 minus 2 gives us 4. And 1 minus 2 gives us -1. Again, if you add all of these up, if you sum the deviation scores, this should add to 0. This is a cross check to make sure you've done everything right up to that moment, right? So let's make sure this adds to 0. -1 plus -2 is -3. -3 plus another -1 is -4. -4 plus 4 is going to give us 0. So we have done our calculations right thus far. All right, so then what we're going to do is we're going to square those deviation scores. -1 squared is 1, and we're squaring them again to remove the negatives out of the deviation scores. So -1 squared is 1, -2 squared is 4, 4 squared is 16, and -1 squared is 1. So that's going to give us a sum of squared deviations of 22. All right. So the sum of the squared deviations is 22. All right. So that's using the definitional formula, what we've been using thus far in order to help us calculate the variance and the standard deviation. So now how does that look if we use the computational formula? All right. So let's see. So in the computational formula, it's best that we organize it in this way. So you're going to make 2 columns, right? One is going to be just the X scores, and we're going to add up the X scores, right? So 1 plus 0 plus 6 plus 1 gives us 8. All right, and then we're also going to square those X scores. So 1 squared is 1, 0 squared is 0, 6 squared is 36, 1 squared is 1, and we're going to add those up to give us the sum of the X scores squared. So that gives us 38. And then we're just going to plug it in to this equation right here. So on this side, we have the sum of the X scores squared, right? That's 38. And in this, we have the sum of the scores, 8. And we're going to square that. So that leaves us with 38 minus 64 over 4. We're going to simplify. So 64 divided by 4 is 16. 38 minus 16 gives us 22. All right, gives us 22. And so 22 is the same number that we got using the definitional formula. Again, those formulas are equivalent. If you get a different number in doing those 2 formulas, you messed up somewhere. You need to go back and retrace your steps. Okay. So now we're going to put some symbols to this because we have to simplify when we are talking about population variances and standard deviations, et cetera. All right. So essentially the formula for the variance, right, explicitly is going to be the sum of squared deviations divided by the population of scores. And the standard deviation is just going to be the square root of the variance. All right. Square root of the variance. So again, the variance is the average of the squared deviations. So we're going to identify the population variance with a lowercase Greek letter sigma, right? We've been using the uppercase sigma, but when we, the lowercase sigma looks like this little thing right here. So sigma squared equals the population variance. All right, that equals the population variance. All right, now the standard deviation is the square root of the variance. So we identify it with a lowercase sigma just by itself. All right, so anytime you see this, that means that we're dealing with a population standard deviation. If we see the sigma squared, we're dealing with a population variance. All right, so let's do some problems. All right, let's do some problems. Let's see. Okay, let's see here. I want to make sure I don't have anybody on the line. I want to make sure that you are seeing the screen. So let's do this one more time. Okay. So in this first question right here, right, it says find the sum of the squared deviations, or SS, for each of the following populations. All right. So note that the definitional formula works well for one population, but the computational formula works better for the other. All right. Let's see. We are going to we're going to start with population 2. All right. And this one, we're going to use the definitional formula because the mean it ends up being a whole number. So it's easier to use the definitional formula, right? So let's work on that. All right, so let's move down. All right, so the numbers that we had for that is 6, 4, 2, 0, 9, and 3. Let me just reconfirm that. Yes, all right, those are the numbers. Okay, so that was the first step. The second step, again, is we're going to calculate the number of scores, which is 6, right? We have 6 scores. And then we're going to calculate our sum of scores. So 6 plus 4 plus 2 plus 0 plus 9 plus 3 is going to give us 24. All right, it's going to give us 24. And then we go to step 4 to find the mean, right? So the mean is going to be the sum of those scores. The population mean is going to be the sum of those scores divided by the population of scores, which is 6. So 24 divided by 6 is going to give us 4. All right. So then we're going to take that mean and we're going to subtract it from each of the scores in our population. So 6 minus 4 gives us 2. 4 minus 4 gives us 0. 2 minus 4 gives us -2. 0 minus 4 gives us 0. I'm sorry, let's see. Sorry, 0 minus 4 gives us -4. 9 minus 4 gives us 5. And 3 minus 4 gives us -1. Now, as a cross check, if we add all those up, it should add up to 0, right? The sum of these deviation scores. So -2 plus -4 equals -6. -6 plus -1 equals -7. 2 plus 5 equals 7. So 7 plus -7 gives us 0. So we are on the right track here. So let's continue. The next step is that we are going to square those deviation scores. All right. So 2 squared gives us 4. 0 squared gives us 0. 2 squared gives us 4. -4 squared gives us 16. 5 squared gives us 25. And -1 squared gives us 1. In step 7, it's going to ask us to get the sum of the square deviations. Right? We're going to add up all those square deviations. So 4 plus 0 plus 4 plus 16 plus 25 plus 1 is going to give us 50. So our sum of square deviations for this particular problem is 50. All right. And so let's work on the next problem, right? So in the population 1, the numbers were 3, 1, 5, and 1. For this one, it's easier to use the computational formula because the mean turns out to be, turns out to be a fraction or a decimal. All right. So that's a little bit harder to work with due to things like rounding error. All right. So let's work on that. So our scores are, right? Our scores are 3, 1, 5, and 1, right? And so what is the sum of all of those scores? 3 plus 1 plus 5 plus 1 gives us 10. And how many scores are there in our population? There are 4 scores. All right. Okay. So then our next step, right, is going to be to square those scores. So we have 9, we have 1, right? So 3 squared is 9, 1 squared is 1, 5 squared is 25, and 1 squared is 1. All right. And so the next step is that we're going to add up all of those squared scores. So 9 plus 1 plus 25 plus 1 gives us 36. All right. And then we're going to plug everything into our equation, right? And that is going to give us 11. All right. Because we plug right here, we plug what the sum of the squared scores is 36. So we plug 36 right here. Then we're going to square our sum of the scores, which would be 100 over 4. So 100 divided by the number of scores, which is 4. So 100 over 4 is 25. So 36 minus 25 gives us 11. All right, gives us 11. All right, so let's continue with answering those questions. All right. All right, so we're not going to do number 2. I don't want you to sketch histograms and estimate the value of the standard deviation. I don't think that's important enough to do. But we can do the second question, right? The second question is to calculate the sum of squares, the variance, and the standard deviation for these scores. Let's see. Well, Well, let's see, we can skip that question too. We kind of already went over the standard deviation of variance. Okay. All right. So here are the answers to these questions. All right. Let's see. Okay. So the next questions are: decide if each of the following statements are true or false. So true or false, the computational and definitional formulas for sum of squares sometimes give different results. Well, that is going to be false, right? The computational formula is an equivalent algebraic formula to the definitional formula. So the results are going to be identical. True or false? If all the scores in a data set are the same, the standard deviation is equal to 1. Well, that's going to be false. We already had a question kind of asking us that. If all of the scores in the data are the same, then the mean is equal to those scores. And so the standard deviation is measuring the average distance a score is from the mean. If all the scores are the same and the mean is the same as the scores, then there is no distance from the mean. So the standard deviation would be 0. It would be 0. All right, and so here are the answers to that. And so this one asks is, what is the standard deviation measure? All right, so the standard deviation is measuring the average distance of a score from the mean. Average distance. Okay, so thus far, we have been calculating the standard deviation and the variance for a population. But most of the time, we are going to be using a sample. So we need to know how that looks. So again, the goal of inferential statistics is to draw general conclusions about a population. Essentially, inferential statistics. We're inferring something about the population by using a sample. All right. And so again, it's based on limited information. The sample is a smaller subset of the population. Right? So samples are going to differ from the population that they came from. All right. We noticed that in week 1 when we talked about the sampling error. All right. So samples tend to have less variability than the populations that they came from. So if we computed the variance and the standard deviation in the same way as for a population, it would give us what we would call a biased estimate of the population values. So we can't measure it the same way. So think about this, right? Here is, let's say that this is the population of all of the students at Bethune-Cookman University, right? This population distribution right here, this normal distribution. If we were to take a sample, right? Let's say I took everyone's height from this class. That's the variable that we were looking at. So everyone's height in my statistics class. This is what this would look like. This is the sample variability, right? And this sample variability is going to have less variability than the population variability, right? Because the population is using everybody to calculate the average height, right? So in our statistics class, right, we don't have a whole bunch of people from, let's say, the basketball team, right, which are going to be way taller. They're going to be like my size and taller, right? We also don't have people who who have dwarfism, right? So we have less variability. We have less variability in our sample than is present in the population, right? And so usually the bias, right, is in the direction of underestimating the population value rather than being right on the mark. So how do we correct this? We have to change parts of the formula to correct for this. So the sum of squares is computed as before. We can use the definitional formula and or the computational formula. Doesn't matter. That's going to stay the same. However, the formula for the variance has what is called n minus 1. So the sample size, right, because we're dealing with a lowercase n, the sample size minus 1, rather than the population of scores, or capital N, in the denominator. And the notation is going to change, right? Instead of using the lowercase sigma to denote a standard deviation, we're going to use a lowercase s to indicate a sample standard deviation. So the formulas for the variance of a sample is going to be the sum of squares divided by the sample size minus 1. So sample variance of a sample is going to be s squared. To get the sample standard deviation is going to be this taking the square root of the sample variance. So let's see some problems. Well, before we get to that, so so the n minus 1, right? Let's talk about that. N minus 1 adjustment is there, again, to correct for the bias in the sample variability, right? So the effect of the adjustment is to increase the value that you obtain. When you divide by a smaller number, n minus 1 instead of just n, it's going to produce a larger result and makes the sample variance more accurate and an unbiased estimator of the population variance. So in terminologically speaking, all right, the sample variance is sometimes called the population variance. The sample standard deviation is sometimes called the estimated population standard deviation. So when you have only a sample to work with, the variance and standard deviation for the sample are going to provide the best possible estimates of the population variability. So now with that being said, let's look at some practice problems using these sample. All right, so now we're working with, this is a sample of scores, right? And we're going to be using the computational formula. So here are the scores. We're going to add up all those scores. That gives us 52. We're also going to square those scores, right? 4 squared is 16, 6 squared is 36, 5 squared is 25, and so forth. And that's going to give us 386. And then we just plug it into this formula right here, right? To get our sum of squares. So 386 minus 52 squared over 8 gives us a sum of squares of 48. Now, if we're using a sample. If we wanted to get the sample variance, we would plug it into this formula right here. So we put the sum of squares right here, which is 48. And the sample size is 8, right? But we are going to go 8, the sample size minus 1. So 8 minus 1 gives us 7. So 48 divided by 7 gives us 6.86. And that is the sample variance. And if we wanted to continue to get the sample standard deviation, right? S stands for sample standard deviation. S squared stands for sample variance, right? We would just take the square root of the sample variance. So the square root of 6.86 gives us 2.62. All right. And so that is our sample standard deviation. All right. So let's talk about the sample variability and what are called degrees of freedom, which is something you're going to be using, especially the degrees of freedom for the rest of this class. All right. So the population variance, the mean is going to be known, right? If we calculate the population variance, it means that we have collected the measurements of everyone in the population on a particular variable and gotten a score for it, and then we added up the score and calculated the variance, right? And so the deviations are computed from a known mean. We have the information for the mean already, so we know the deviation scores, all right? However, we're usually not going to be using a population. We're going to usually be using a sample. Now, a sample variance is an estimate of the population. And in this case, the population mean is unknown, which the majority of the time when we're doing studies, we do not know the population mean. And so using the sample variance is going to restrict our variability, like I talked about with the different heights, right? The population of the heights is very, very broad, has a lot of variability, but the population of the heights for our class in statistics is limited in comparison. So we have what are called degrees of freedom. So the number of scores in the sample that are independent and free to vary. That's what the degrees of freedom mean, right? So the degrees of freedom, when calculating the standard deviation and the variance for a sample, is going to be the sample size minus 1. All right. So with the sample, the value again of the population mean is unknown, and you must measure distances from the sample mean. But because the value of the sample mean varies from one sample to another, right, you must first compute the sample mean before you can begin to compute the deviations. However, calculating the value of the sample mean is going to place what is known as a restriction on the variability of the scores in the sample. So let's talk more about this. So suppose we select a sample, right? It's a sample because we have the lowercase n, a sample of 3 scores, and compute the mean of 5, right? The first 2 scores in the sample have no restrictions, right? They are independent of each other and they can have any possible value. For this demonstration, assume that we obtained x equals 2 for the first score and x equals 9 for the second. At this point, however, the third score in the sample is restricted, right? If we already calculated the mean and it's only 3 scores, right? And we know 2 of the scores. One of the scores is 9, the other score is 2. Well, the third score can't vary, right? The third score has to be 4 in order to satisfy the calculations, right? Because 9 plus 2 is 11, right? And so in order to get the sum of the scores, it would be 3 times 5, which is 15. Well, if 9 and 2 is 11, right, then we need one more score. Well, that means that the third score's only possibility is going to be 4. All right. So that last score lacks the variability that the first two scores had. These first two scores, in order to get to 15, these first two scores could have been anything. We could have had a 1,000 over here, and then we could have had what, 195. And once we added those together, what, that's 1,000, 1,095, right? In order to get our score, we would just need to make sure our scores, all three of the scores, add up to 15, right? But if we know the first two scores, the third score has a restriction. It has to be a certain score in order to satisfy the equation. All right. So again, the first two out of the three scores were free to have any possible values, but the final score was dependent on the values chosen for the first two. So in general, with the sample of scores, the first sample size -1, or degrees of freedom of scores, are free to vary, but the final score is restricted. So as a result, the sample is said to have n-1 degrees of freedom, right? So it's a complex kind of idea, but we're going to be using it a lot in order to help us in trying to use samples to get generalizations about populations. Okay. So let's do some questions. So a sample of 4 scores has a sum of squares of 24. What is the variance, right? So the sum of squares is 24. The variance, and the sample size is 4, right? And they're asking, what is the variance, right? Well, the variance for a sample, so variance for a sample is s squared. The formula for that is going to be sum of squares divided by the number of scores that we have in a sample minus 1. So that's going to be 24 divided by 4 minus 1, which is 3. So 24 divided by 3 gives us 8, right? So our sample variance is 8. All right, so decide if each of the following statements are true or false. True or false? A sample systematically has less variability than a population. Well, that is going to be true, right? Extreme scores affect the variability, but are less likely to be included in a sample. So think about extreme scores, meaning in the population, we have, basketball players who are 6'9", 6'10" at Bethune-Cookman, if we're measuring height, and we have people who are incredibly short as well. But in our class, we don't have anybody who's a baller, and we don't have anybody who is a little person, all right? So we are going to have less variability in a sample. Second question asks, true or false? The standard deviation is the distance from the mean to the furthest point on the distribution curve. Well, that's false. The standard deviation is going to extend from the mean approximately halfway to the most extreme score. I'm going to talk a little bit more about that. All right, so let's talk more about the sample variance as an unbiased statistic. All right, so the unbiased estimate of a population parameter. So the average value of a statistic is going to be equal to the parameter. This is going to be an important point. All right, if we average all of our statistics, right? So that means we add up our statistics, all right, and then divide by the number of statistics that we have, it's going to be equal to the population parameter. All right, so the average value is going to use all possible samples of a particular size, right? So let's say if we had a sample with a sample size of 2, all right, if we were to collect all of the possible samples in the population, right, with a sample size of 2, and we calculated, let's say, the mean, right? So we calculated the mean with all the possible samples of a sample size of 2. If we added up all of those sample means and then divided it by the number of sample means that we had, it is going to equal the population parameter of the mean for the population. All right, so the average value of a statistic is equal to a parameter. Now, the corrected standard deviation formula, right, dividing by n minus 1, is going to produce an unbiased estimate of the population variance. The biased estimate of a population parameter is going to systematically overestimate or underestimate the population parameter. So we don't want to do that. That is why we take the degrees of freedom, because if we do it correctly and we take the degrees of freedom, if we average out all of the average value of the statistic that we are getting, we would get, it would be equal to the population parameter. All right. So some more about the variance and the standard deviation. All right, so the means and the standard deviations are going to be very helpful in making sense of graphs and their accompanying distributions. The mean and the standard deviation together are going to give us very useful descriptive statistics for characterizing distributions, right? But essentially telling us how they look, how they operate, and a couple of different rules of thumb. All right, so for both populations and for samples, it's going to be easy to represent the mean and the standard deviation. All right, the way we do this is that there's going to be a vertical line in the center, drawn in the center, which is going to denote the mean, either the sample mean or the population mean. And then we're going to have horizontal lines to the left or to the right, and that's going to tell us the distance of one standard deviation. All right, so let's see how that looks. So this is a normal distribution, right? For a population of scores, right? Because we have the relative frequency, we have the smooth curves, right? This is it's called a bell curve or a Gaussian distribution, or just a normal distribution. So right here, we have this line right here. This is telling us that this is where the mean is at, the population mean, right? And underneath it, we have the mu symbol, which means the population mean. So the population mean equals 80. Over here, jutting out from the left, we have this line, right? And that is giving us our population standard deviation. Standard deviation. And so our population standard deviation is going to be 8. All right. So that's our population standard deviation. Now, if we are looking at a sample, right, sample distribution, right? In this one, we have 4 scores in our sample. So one person scored a 13, 2 people scored a 15, right? So we have 13, we have 2 people who scored a 15, we have 1 person who scored a 17, and we have 2 people who scored an 18, right? So if we average that all out, the sample mean is 16. We know it's a sample mean because we have that capital italicized M. All right. And when we calculated the standard deviation, we got 2, right? So in this one, the mean is right here again. This denotes that this is the sample mean, right? It's that vertical line. And jutting out from the left and from the right is the standard deviation, meaning that, again, the standard deviation means on average, how far away are scores from the mean, all right, on average. And so that is how we look at these, either in a sample either in a population distribution or in a sample distribution using a histogram. Okay. So just like what we had with the mean, we also have transformations of scale for the standard deviation. So if we add a constant to each score, remember a constant is something that we do, that we apply to each of the scores that we have. Well, if you remember back to the previous chapter, the mean is going to be changed, right? If we added a constant of, let's say, 2 to each score, well, the mean is going to change by that same constant. So in that case, it would be changed by 2. We would add 2. However, if we add a constant to the standard deviation, right? If we add a constant to each score, the standard deviation is going to remain unchanged. All right, it's going to remain unchanged. All right, so now why is that? Well, that is because the standard deviation is only measuring how far away a score is on average from the mean. If we apply the same change to each score in our distribution, then the mean has changed, but the distance each score is from each other and from the mean has not changed. So the standard deviation is going to remain the same. All right. However, if we are multiplying each score by constant, let's say if we multiply each score times 2, again, the mean is going to be changed, right? The mean is going to be changed by that same constant. And in this case, the standard deviation is also changed. So the standard deviation is going to be multiplied by that constant. All right, it's going to be multiplied by that constant. So if we multiplied each score in our population or in our sample by 3, then we're just going to also, to get a new standard deviation, we're going to multiply our old standard deviation by 3. And that'll give us our answer. Okay. So the standard deviation and descriptive statistics. right? So a standard deviation describes scores in terms, again, of a distance from the mean, all right? You could describe an entire distribution with just two numbers, right? In this case, the sample mean and the sample standard deviation. Or we could, describe an entire distribution with the population mean and the population standard deviation. Reference to both is going to allow the reconstruction of the measurement scale from just these two numbers. So we can know a lot about our distribution by just having the sample size, the sample mean, and the sample standard deviation, or the population size, the population mean, and the population standard deviation. So in this one, the mean is 36. That's where that vertical line is, right? The standard deviation is 4, right? So on average, right, we expect a score to be 4 distance points away from the mean. So 1 standard deviation above the mean is 40, right? It's 40. 36 plus 4 is 40. If it were 2 standard deviations away from above the mean, well, that's 40 plus another 4, so 44. And if it was 3 standard deviations above the mean, well, that's another 4, right? So that would be right here, be 48, be right here. All right. And going the opposite way, right? 1 standard deviation below the mean is 36 minus 4, which gives us 32. 2 standard deviations below the mean is right here at 28. And 3 standard deviations below the mean is 24. All right. Now, some rule of thumbs that we're going to work on more in the chapters to come. All right, with this concept of standard deviation is that as a rule of thumb, 70% of the scores in any normal distribution, whether it's a population or if it's a sample, are located within a distance of 1 standard deviation from the mean. And almost all of the scores, roughly 95%, are within 2 standard deviations of the mean. So in this example, right, the standard distance from the mean is 4. That's the standard deviation. So your image should have most of the boxes within 4 points of the mean and nearly all of the boxes within 8 points of the mean, right? And so when we did this, right, 8 points from the mean, right, we had the majority of the boxes are right here. So 70% of our scores are going to be within 1 standard deviation, either above or below the mean. And 95% of our scores are going to be within 2 standard deviations of the mean. All right. So we're going to say, right, that if we get a number, right, if we get a score that is more than 2 standard deviations, either above the mean or below the mean, we are going to call that score an extreme score. It's an extreme score. All right, that's going to be very important, especially for the next chapter. All right, that's going to be an extreme score. So variance and inferential statistics. So the goal of inferential statistics is going to be to detect, again, meaningful and significant patterns in research results. It's the whole purpose of why we're doing this stuff, right? To make generalizations about a population, to get useful information. The variability in the data influences how easy it is to see patterns, all right? And so those of you who have already taken research methods, you know how variability and variance can make it harder to see patterns in your data, right? So high variability obscures patterns that would be visible in low variability samples. So what do you mean by variability? You mean how widely scattered are scores from the mean? If the scores are very, very far from the mean, then we have high levels of variability. If scores are very close to the mean, we have low levels of variability, right? If the scores are all wildly far away from each other, again, that is also high variability, all right? Variability is sometimes called the error variance, but we're not going to use that much in this particular class. So here is give me a second. Here is sort of an example of how variability obscures patterns in the data. So here are two experiments with two different treatment groups. So here's experiment A, and here's treatment group 1 and treatment group 2. And then here's experiment B, and here's treatment 1 and treatment 2. All right. So the difference in between the scores, so let's say there's 4 people in each of these experiments, right? The difference in the scores between treatment 1 and treatment 2, they're pretty obvious in experiment A, right? Like 35 to 39 is a difference of about 4, 34 to 40 is a difference of about 6, 36 to 41, difference of 5, difference of 5, right? So the difference between these two treatments, right, is about 5 points, right? 5 points. But now if we move on to experiment B, the difference between treatments are very hard to easily quantify, right? So, and that's because these have high variability, right? The scores are scattered more. So 31 to 46, 15 to 21, 57 to 61, 37 to 32, right? These scores are all over the place. All right. So what does that look like when it's graphed? Right? It gets more confusing. Let's see. So if we graphed experiment A, right, we can clearly see that there is a 5-point difference between the two, right? It's very neat, very uniform. We can see that there's a difference between the two treatments. But if we go to experiment B, well, it's, even though the means are still the same, right? The means are the same as this one, as treatment A, experiment A. When we plot out our histogram, the scores are all over the place. So we can't tell we can't find patterns in the data. And so if we can't find patterns in the data, it's hard to make conclusions about what's going on. And all of that is a problem that has to deal with, in this case, the high levels of variability, meaning that the scores are far away from each other and far away from the mean. So there's a very large standard deviation. Okay. All right. So we're going to skip number one, right? But for number two, right? In a population with a mean of 50 and a standard deviation of 10, would a score of x equals 58 be considered an extreme value? All right, far out in the tail of the distribution? Well, let's see. So the way we would answer that question is let's draw a population distribution with all the information that was given. So here's the population distribution, right? Here is where the mean is. The mean is 50. Our score is 58, right? The standard deviation is 10. So what we said was an extreme score is going to be a score that is 2 standard deviations or more away from the mean. So in this one, if the mean is 50 and the standard deviation is 10, one standard deviation, I guess, above the mean would be 60. 2 standard deviations above the mean would be 70, right? So the score that we have is 58. 58 is less than 1 standard deviation above the mean because the standard deviation, the first standard deviation above the mean is 60. So this would not be an extreme score if the standard deviation is 10, right? But let's say that now instead of the standard deviation being 10, right? Let's say the standard deviation has now been changed to 3. So let's draw all our information again. So again, the population mean is 50. The standard deviation this time is going to be 3, right? And we have a score of 58. So 1 standard deviation above the mean is 50 plus 3, which is 53. 2 standard deviations above the mean would be a score of 56. Our score is 58. Now, like I said earlier, we are going to consider an extreme score to be 2 standard deviations or more away from the mean. So 58, a score of 58 in this instance would be more than 2 standard deviations away from the mean. And I've been using numbers that are going above the mean, but you could also do this by going below the mean, right? So if I had, so if my score was, let's see, 42, if I had a score of 42, well, 42 would be an extreme score as well, because it is more than 2 standard deviations below the mean, right? So the first standard deviation is 50 minus 3, which would be 47. And then 2 standard deviations below the mean would be 44, right? But if our score is 42, 42 is 2 or more standard deviations below the mean, which would indicate to us that that is an extreme score. It's extreme because, right, 70% of our scores are going to be within 1 standard deviation from the mean. And 95% of our scores are going to be within 2 standard deviations from the mean. So if we have a score that is beyond 2 standard deviations, well, we are going to again consider that to be an extreme score. All right. So the third question, a population has a mean of 70 and a standard deviation of 5. If 10 points, right, were added to every score in a population, so a constant of 10 plus of 10. All right. What would be the new values for the population mean and the standard deviation? Well, the mean is going to change by the constant, right? If we're adding. So we added a score of 10 to each score. So we would add a 10 to the population mean. That would bring the population mean to 80, right? But the standard deviation is going to remain the same. So the standard deviation is still going to remain 5. Now let's look at B. If every score in the population were multiplied by 2, right, what would be the new value for the population mean and the standard deviation? Well, for the mean, if we multiply by a constant each score, it's going to change the mean by that same constant. So if the mean was 70, the new mean is going to be 70 times 2, which gives us 140. The standard deviation is also going to be changed by if we multiplying by a constant. So the standard deviation, if we're going to multiply by 2, would be 5 times 2, which would give us 10. 10 would be the new standard deviation. All right. And so here are the answers. And so that's another question. So a population has a mean of 6 and a standard deviation of 2. Again, if each score is multiplied by 10, what is the shape of the resulting distribution, right? So it would turn into this. We would multiply the population mean by 10 and the standard deviation by 10 if we're multiplying by a constant of 10. So we would turn into 60 is the new population mean, and the standard deviation is now 20. All right, so the next one is a true or false, right? And it goes decide true or false. A biased statistic has been influenced by researcher error. Well, that's going to be false. The bias is going to refer to the very systematic effect of using sample data to estimate a population parameter. All right. Second question, true or false? On average, an unbiased sample statistic has the same value as the population parameter. So the key point of this is on average. If we average all of the sample statistics, we are going to get the population parameter. It's going to be equal to the population parameter. So that is true. All right, that is true. Okay. So now, when you are reading research, right, or when you're creating your own research, all right, there are ways to identify what is being said through statistical notation. So in many journals, especially those following the APA style, which is what you're going to be using, since most of y'all are psych majors, they're going to use the symbol SD is used when talking about the sample standard deviation. And for example, the results might state, hey, children who viewed violent cartoons displayed more aggressive responses, the mean, the sample mean is 12.5, and the standard deviation is 3.70. All right. And so that's how it would look if you were reading it in the literature. Now, how would it look if you were using SPSS? Now, SPSS is a statistical software that we are going to be using a lot in the upcoming weeks. All right. If we were to calculate some descriptive statistics, which is going to be one of your first computer assignments, well, this is how it would look most of the time. So this right here is going to be what the variable is, right? This right here, this capital N, right? In SPSS, they won't have a lowercase n, right? So you'll have to know if you're dealing with either a population or with a sample. This is telling you how many scores that you have. So this is the sample size, all right? This is the range. We didn't go over the range, but that's another measure of variability. This is the highest score. This is the lowest score, the minimum. And this is the highest score in your distribution of scores. Here is the mean, right? This literally says mean. And when you're talking about the standard deviation, it's STD dot deviation. All right, so standard deviation. And this is the variance, the sample variance. All right, so that's how it would look in an SPSS. All right, this one is going horizontally, but you could see it vertically. But if you see it vertically, all of these headings would still be the same. All right. All right. And so that brings us to the end of this particular chapter, right? And this lecture. I thank you for sticking around with this. If you have any questions, please do not hesitate to call me or hit me up on email or Canvas, or come for assistance during my office hours. You can come for this particular class or any other class that you have with me, or for any other issue, such as advising if I am your advisor. All right, and you have a great day. Peace.